Okay, let's get started. So in the last lecture, we were talking about Brownian motion, and just to refresh your memory, I've put the definition up there, the first definition. As you recall, we saw two definitions, and just one little change from what I wrote last time. I've put stationary in brackets this time. So if you're sort of alert, you'll have noticed that actually this condition together with independence implies stationary. So it is true that it has stationary independent increments, but you don't strictly need it to be part of the definition because it follows from those two properties. But it's kind of handy to know it's there, just to emphasize that it does have this the stationary property of the increments. Okay, so before I move on to there was one further property I wanted to talk about Brownian motion before we move onto the next chapter. Does anyone have any questions about anything we discussed last week? Okay, so I want to talk about path properties of Brownian motion, and first of all, just give a definition of Holder continuity, which I think many of you may have seen already. Okay, so what does it mean for a function to be Holder continuous? So if we have a function f from some real interval ab into the reals, and we say this function is gamma Holder continuous, at some point x in AB, if there exists some constant c strictly positive, such that f of x minus f of y is less than or equal to that constant c times x minus y to the power of gamma for all y in the interval AB. Okay, so as I said, I think probably quite a few of you will have seen this definition before if you've done any kind of functional analysis module. If you haven't seen this one, it's very likely that you've seen Lipschitz continuous, which is what you would get if gamma was equal to 1. And Lipschitz continuity is slightly weaker than being differentiable, and Holder continuity, again, if gamma is less than 1, is sort of weaker than being Lipschitz continuous. So what you can see by looking at this, if this is true for any gamma greater than 0, we definitely have continuity in x and y, but it's not as strong as Lipschitz continuity. So it's stronger than just having continuity, but it's not as strong as Lipschitz continuity or differentiability. So it's a way to sort of indicate what kind of continuity you've got. And obviously we can take gamma to be bigger than 1, and when we get sort of stronger and stronger forms of continuity there. Okay, so what kind of continuity does Brownian motion have? I'll tell you this in a minute, but first just need a sort of preliminary theorem which we'll use, which is called Kolmogorov's continuity theorem. Okay, so suppose that x is any stochastic process. It's a stochastic process such that there exist constants c, alpha, and beta, all strictly positive, for which the expected value of xt minus xs to the power of alpha is less than or equal to c times t minus s to the beta. Well, then we know that there exists a modification x tilde of x. Well, what does that mean? That means that probability that xt is equal to xt tilde is equal to 1 for all t greater than or equal to 0, such that x tilde is continuous and the paths of x tilde are gamma Holder continuous for all gamma strictly less than 1/2. Okay, so what does this theorem tell us? Well, we start off with a condition which looks a little bit like Holder continuity, except we've got expectation on the left-hand side. So if we didn't have expectation, you could just divide through by alpha, and that's essentially telling us, oh, sorry, this shouldn't say half. This should say, sorry, 0 less than gamma less than beta minus 1 divided by alpha. Sorry about that. Okay, so if we didn't have the expectation over here, and you just sort of took power of 1 over alpha on both sides, that would precisely tell us that this was a Holder continuous process with parameter gamma being beta divided by alpha. But the trouble is we have the expectation here, and this is just telling us something about the average behavior of this process. But we want to know something about every single sample path. And so there's two things that you need to do. The first thing is you can't just immediately assume things about the sample path. If you know something about the average, you can always have a property zero space where the sample paths are very, very badly behaved. And so that's when we need to restrict to some modification where the sample paths are going to be good. So we can construct some kind of modification where we can choose the paths that are going to be good. So for any modification, I could take just a handful of omegas and just replace those with being bad paths, and that would still have the same expectation and would satisfy this property over here. But the point is I can choose a modification which has good sort of nice paths, continuous paths. So that's the first point, is we need to move to modification. And the second one is it actually costs us to get rid of this expectation. So we can't say that x is Holder with parameter beta divided by alpha. The best we can do is beta minus 1 over alpha. So it costs us a sort of minus 1 over alpha and a little bit less, because this is a strict inequality. And that's the price of getting rid of the expectation. Okay, so I'm not going to prove this theorem here, but it's actually not too difficult to prove. Essentially, what you want to do is you want to construct the process on the dyadic rationals. So you just sort of go through the dyadic rationals and you construct a countable sequence of values of x tilde on the dyadic rationals that have the Holder continuity property that you want, and then you define your x tilde by taking limits of the dyadic rationals. And you can show that you use the Borel-Cantelli lemma to show that you can do your construction on the dyadic rationals, and it's Borel-Cantelli that costs you this sort of minus 1 over alpha. Okay, so I won't prove this, but essentially you do it on the dyadic rationals, and then just extend continuously to the reals. Okay, well, it's clear that something like this is going to we can apply it to Brownian motion, because we just need to do an expectation computation, and we know the distribution of the increments of Brownian motion. It's just normal 0 t minus s. Okay, so what happens if we apply this theorem to to Brownian motion, well, here's our corollary. Corollary is that Brownian motion so is gamma Holder continuous for all gamma less than, and let's just see what people's intuition is like. Anyone got any ideas what value I'm going to put in here? It's 1/2. Yeah, I guess you could have guessed that because I accidentally wrote the 1/2 over there. So the answer is it's gamma continuous with gamma less than 1/2. So in particular, it's a continuous function. It's definitely not going to be Lipschitz continuous, and it's not going to be differentiable, which is sort of interesting in a way. You know, we've got when you draw pictures of continuous functions, they tend to always be differentiable, at least piecewise differentiable. Here we've got something that's continuous, and it's not. It's actually got very weak continuity properties. It's not differentiable anywhere. Okay, so how do we prove this? Well, the trick is we need to pick our alpha carefully. So if you pick your alpha right, you can get a strong result. If you pick your alpha wrong, you get a weak result. Well, let's just take alpha to be some integer m. So for m in the natural numbers and t bigger than s, what's the expectation of bt minus bs to the power of m? Well, we know the distribution of this. This is just a normal 0t minus s random variable, and so this is exactly the same as the expected value of the square root of t minus s times z to the power of m, where z is just a standard normal 0, 1 random variable. Okay, well, we can just pull out the square root t minus s to the power of m, because that's just a constant. And so this is equal to t minus s to the power of m over 2, expected value of z to the e, z to the m. And this is just a constant, right? This is just take some normal random variable and just do this computation. It doesn't matter what the answer is constant. There's nothing in here that depends on t or s. And so this is just equal to some constant. It does depend on m, but it's still a constant times t minus s to the m over 2. And so immediately by Kolmogorov's continuity, we just need to put beta equals m over 2 and alpha equals m. And so straight away we know that by Kolmogorov, we have that Brownian motion is gamma Holder continuous for all gamma less than, well, if we do m divided by, so m over 2 divided by m, we get m over 2m, and the minus 1 over 2m becomes a minus 2. So minus 1 over m becomes minus 2 over 2m. So this is true for all gamma strictly less than m minus 2 over 2m. But we chose m completely arbitrarily. We could have chosen it to be anything that we wanted. And so in particular, if you let m go to infinity, we can get arbitrarily close to gamma. And so it's Holder continuous for all gamma strictly less than 1.5. So the result follows by m going to infinity. Okay, so that's the proof that the Holder coefficient of Brownian motion is strictly less than 1/2. And just a couple of remarks about this result. So in fact, you can show that the modulus of continuity of Brownian motion is square root of 2h log h to the minus 1. So what does that mean? If we look at bt plus h minus bt, that's less than or equal to square root of 2h log h inverse. So that's the sort of strongest result that you can prove. And again, if you want to see how to prove that, there's quite a few textbooks on Brownian motion that prove that. Probably the easiest one to understand is maybe I think it's Yuval Perez and Peter Morta's book on Brownian motion, and definitely has that result in it. And then the second remark I want to say is that this is sharp. So in fact we have that Brownian motion is not gamma Holder continuous. For any gamma strictly bigger than 1/2, and in particular almost surely the trajectory of Brownian motion is nowhere differentiable. So if you take any small interval, you can show that the Holder continuity doesn't hold for any gamma bigger than 1/2. And so you can show that there's no interval on which Brownian motion is differentiable. Okay, any questions on that? Okay, so that's essentially the end of the chapter on Brownian motion. So that was the only sort of bit I just unfortunately didn't fit into the end of the last lecture. So now we're going to move on to the next chapter, which is on Martingale. So new chapter on Martingales. Okay, so a martingale is a special type of stochastic process, and it's one that is going to turn out to be pretty fundamental when we go on to construct the stochastic integral. And informally, a martingale can be thought of as a stochastic process that models a sort of gambler's wealth if you're playing a fair game, so if you're constantly betting some money in the kind of game where your losses and your winnings on average always balance out. So that's the sort of idea of a martingale. It's a fair game, and I'll give you the formal definition later on in this lecture. But before we do the formal definition, we just need a little bit of background measure theory and conditional expectation. Okay, so the first thing that we need to know is what a filtration is. Okay, so here's our definition. So given an indexing set T, which is some subset of the non-negative reals, a filtration is a collection of sigma algebras so we're going to use the double bold sort of F to represent it. So it's a set of sigma algebras Ft corresponding to T's in the index set, satisfying Fs is a subset of Ft for all 0 less than S less than or equal to T. Okay, so I think in the questionnaire you've said you've all done measure theory, so everyone's happy with the sigma algebra. Is that right? Okay, so it's a whole family of sigma algebras indexed by our index set. So for every time in our index set we have a different sigma algebra, but the sigma algebras are increasing in time. And you can sort of think of a filtration in a way as a sort of a flow of information. So at time S, the sigma algebra consists of those events which you know about at time S, and then which you can tell whether they're true or not at time S, and then as time increases, there's more and more events that you can determine whether they've occurred or not. And so as the amount of information that you have increases in time, the number of events that you can tell whether they've occurred or not also increases in time. Okay, so there's a couple more definitions. This next one is adapted. So a stochastic process xt for T in some indexing set T is adapted to a filtration if xt is ft measurable for all t in our indexing set, i.e. what does that mean? That means that the event xt less than or equal to x lies in our sigma algebra for all x in R and t in T. Okay, so yeah, I think this is just your standard definition. So in particular, you can tell if you know your stochastic process up to time t, this event of whether it's bigger or smaller than something is an element of your sort of sigma algebra corresponding to t in that filtration. And then next definition is a natural filtration. So given a stochastic process X, the natural filtration is the smallest filtration F for which xt is adapted to x. And in fact, we can show, so it can be shown that the natural filtration is given by Ft is the sigma algebra generated by the random variables xs for 0 less than or equal to s less than or equal to t. So are you happy with this notation to mean sigma algebra generated by? So if I put sigma and in brackets some random variables, I mean the smallest sigma algebra that contains all of these events for that set of random variables. Okay, and so the key point is if f is the natural filtration for a particular stochastic process, then you can tell whether the event xt less than or equal to, so then you can tell that any event in the filtration, so in the sigma algebra ft within that natural filtration, you can tell whether any event occurred or not just by observing the stochastic process up to time t. So all of the information about whether or not an event occurs in this filtration is contained in the stochastic process itself. So that's what it means by natural filtration. It's a measure of the information that you have up to time t by observing just the stochastic process. Okay, and if you remember in the last lecture, we talked about stopping times, and I gave a slightly informal definition of a stopping time. Now that we have this language of filtrations, that allows us to actually make the definition of stopping time a bit more precise. So here's the formal definition of a stopping time. So a random time t is a stopping time with respect to a filtration if the event t less than or equal to t lies in ft for all t in our indexing set. Okay, so one difference from the definition we had before is a stopping time is with respect to a filtration. So you need to have a filtration in mind before you start talking about a stopping time. In most cases, the natural filtration is the right one to have in mind. So if we talk about a stopping time with respect to a stochastic process, we're thinking a stopping time with respect to the filtration, the natural filtration for that stopping, for that stopping time. And what does this condition over here mean? Well, this means capital T less than or equal to t lying in our sigma algebra means we can tell whether t has occurred by time t just by looking at the information contained in that sigma algebra up to time t. So in particular, if this is the natural filtration, that means we can tell whether t occurred or not by time t just by looking at the path up to time t. And that was the informal definition that I gave in the last lecture. So hopefully you can see why this definition together with what we've put above corresponds exactly to the sort of informal definition that I described before. Okay, any questions on any of that? Okay, so that's essentially the measure theory that you need to know. So next going to move on to the conditional expectation results that we need to know. Okay, and so throughout the section, let's just say, so throughout we're going to take omega Fp is a probability space. Okay, so I won't explicitly mention this, but underlying everything we have a sample space, a sigma algebra, and a probability measure on that sigma algebra underlying everything. Okay, and just a bit of notation. So this is notation for an indicator function. So given an event A in our underlying sigma algebra, the indicator function of A is the random variable and I'm going to use the notation capital I. Some of you might be used to just using a 1 or a double bold 1. There's a lot of different notation around. I'll use capital I from omega to the reals given by indicator function of omega is equal to 1 if omega is in the event A and it's equal to 0 otherwise. Okay, so now we can give our definition of conditional expectation. Okay, so let x be an integrable random variable. Right, what do I mean by that? Expected value of the modulus of x is finite. And this is a random variable on omega Fp. And let G be some subset of F be a sigma algebra. Okay, a random variable Z is called the conditional expectation of x given G. And we write this as Z is equal to expected value of x conditioned on G if it satisfies two properties. So the first one is Z is G measurable. And the second property is that the expected value of Z times the indicator function of A is equal to the expected value of X times the indicator function of A. And this is true for all A in our sigma algebra G. Okay, so when we gave out the questionnaire at the start of the course, we asked who'd seen conditional expectation. Can I just ask who's seen this definition before? And who's seen quite a different looking definition? Okay, so it seems the majority of you maybe haven't seen this definition before. You've seen something a little bit different. Maybe what you'll have seen is something like the expectation of y given x is equal to, say for discrete random variables, sum of x times the probability that, sorry, let's make it sum of. Is that more what people have seen? Okay, so this is a definition that works if you have a random variable that you want to be conditioning on. So if I have two random variables that have a joint distribution in some way, and I tell you what the value of one of the random variables is, then this is a way that tells you how to compute the expectation of the second one, given that you know that the first one takes a particular value. So that should be an x equals x. What we need to do in order to understand martingales is it's not enough just to condition on a random variable. We actually need to condition on a sigma algebra. And so a sigma algebra contains a whole lot of events, and so we need to condition on knowing this whole family of events. And so something like this isn't going to work anymore. So we need a different definition that if our sigma algebra is just the sigma algebra generated by a random variable, then it will agree with this definition. But it allows us to talk about conditional expectation, conditioning on much larger classes of things. So let's just say if y is a random variable on omega fp, then the conditional expectation of x given y is defined by expected value of x conditioned on y is equal to expected value of x conditioned on sigma y. Okay, so this definition allows us to talk about conditioning on random variables, but it allows us to talk about much more. So in particular, we can talk about conditioning on several random variables at the same time, or even uncountably many random variables at the same time. We can talk about a sigma algebra, conditioning on a sigma algebra generated on, say, a stochastic process up to time t, which is what we're going to want to do. Now, one of the things that makes this definition quite difficult to work with, and in fact I would even go so far as to say it's possibly the most difficult definition in probability theory. Why do I say that? Well, because it's a definition that doesn't tell you how to construct the object. So if I have a random variable x and I have a sigma algebra G, this doesn't tell me how to construct the conditional expectation of x given G. It just tells me if I know what the conditional expectation is, or if I have a guess for what the conditional expectation is, the two properties that it needs to satisfy. So it'll tell me if my guess is correct. I take my guess. Is my guess G measurable? Does this property hold? Yes, I guessed correctly. But it doesn't tell me how to actually go about constructing this. And that's what makes it quite a difficult thing to sort of get your head around, because it's a very sort of indirect definition. There's a set of properties that is satisfied by conditional expectation, but it gives you no idea at all how to actually go about constructing it. Okay, and what you can do, as I said, if you take your familiar conditional expectation definition, so for a discrete random variable or for a conditional one using conditional densities, it's not too difficult to actually go through and check that for those old definitions, these two properties do hold. But what do you do if you want a condition on something that isn't actually a random variable, which you already sort of had a definition for? How do I actually do anything with this definition? And it turns out that what you can do with this definition is you can sort of establish a set of properties that conditional expectation need to satisfy, and then using these properties you can sort of manipulate expressions that you know until they go into a form that essentially reduces to conditional expectation with respect to a single random variable, and then you can use your old method. Okay, so what I'm going to do now is I'm going to write down a list of properties satisfied by conditional expectation, and then we'll, when we start sort of working with conditional expectations in our study of Martingales, we'll see how we can manipulate these properties to actually reduce conditioning on a sigma algebra into conditioning on a random variable or something simpler than that. Okay, so here are some properties. So here's our theorem. So properties of conditional expectation. Okay, so let x and y be integrable random variables. And let G subset of F be a sigma algebra. Right, then the following properties hold. So first property is that the conditional expectation of lambda x plus mu y conditioned on our sigma algebra G is equal to lambda times expected value of x conditioned on G plus mu times conditional expectation of y conditioned on G, and that holds for all lambda and mu in the reals. Okay, second property is that the modulus of the expected value x conditioned on G is less than or equal to the conditional expected value of the modulus of x conditioned on G. Third property is if G is just the trivial sigma algebra, so if G is just equal to the empty set and the full sample space, then the conditional expected value x given G is just equal to the expected value of x. Fourth property is if x is G measurable, or equivalently the sigma algebra generated by x is contained in G, and we know that xy is integrable. Then expected value of xy conditioned on G is equal to x times the expected value of y conditioned on G. I'm just going to try and keep a little bit of this definition down here for discussing this theorem. Number 5 is if G prime is another sigma algebra with G prime contained in G, then we can ask about the conditional expectation of the conditional expectation of x conditioned on G conditioned on G prime, and that's just expected value, conditional expectation of x conditioned on G prime, and in particular taking G prime to be the trivial sigma algebra gives expected value of the conditional expectation of x given G is just the ordinary expected value of x. And last one is if sigma algebra generated by x and the sigma algebra G are independent, so what does that mean? Well, that means that if you pick any event in the sigma algebra generated by x and any event in G, then the probability of the intersection of those two events is the product of those probabilities. So those two events, so any event in here and any event in here are independent, then conditional expectation of x conditioned on G is equal to expected value of x. Okay, so what do these properties tell us? Well, the first two just tell us that conditional expectation has these sort of nice properties that ordinary expectation has. So ordinary expectation is linear, ordinary expectation satisfies this triangle inequality, and so these two results just tell us that conditional expectation also satisfies these two nice properties. What about the third one? Well, the third one tells us that if G is the trivial sigma algebra, so in other words, if we have no information, right? If the only events that you know whether they've occurred or not are nothing and everything, then essentially you have no information. So conditioned on being given no information, your expectation is just your old definition of expectation. What about this next one, condition 4? Well, condition 4 tells us that if x is G measurable, then essentially if you look at the conditional expectation of x times any other random variable, you can treat x as though it's a constant. So you can just take it outside your conditional expectation. In particular, if x is G measurable and you just don't have y at all here, then the conditional expectation of x given G is just going to be equal to is just x. So if you know everything about the random variable x, then conditioning on knowing everything about it, you just end up back with that random variable. This one here, number 5, is, I think you might know it as the sort of tower. You might have seen this with your old expectations called the tower rule. And this sort of tells us that we can sort of refine sigma algebras. So if we have a certain amount of information, we can ask ourselves, well, what's the conditional expectation on that amount of information? If we then throw away some of that information, so we now have even less information, so we can condition again and say, well, now I'm conditioning on a smaller amount of information. That would be the same as if we just conditioned on the smaller amount of information in the first place. And so in particular, the smallest amount of information you can have is no information, is just conditioning on this trivial sigma algebra. And if we take the expected value of a conditional expectation conditioned on no information, we just back to it's as though we never had a conditional expectation in the first place. And lastly, again, if we've got that our random variable x is independent of our sigma algebra in the sense that I explained earlier, then conditioning tells you nothing. So you might as well just not be conditioning, and you just get the expectation. Okay, so which are the useful ones? Well, this one is particularly useful, being able to pull out measurable components, because in practice, if I'm conditioning, if I've got some sort of complicated expression and I want to condition, I can somehow decompose my complicated expression into the bits that I already know what the values are, and I can treat those as constants, and then I'm left with something here which is not measurable with respect to this. And quite often, if you do things well, y might be independent. So if you can sort of split a random variable up into a product of a measurable bit and an independent bit, this result says we can pull out the measurable bit, and then this result says, well, if it's got an independent bit, we can just drop the conditioning altogether. And so these two, I think, are probably the most useful, and we'll sort of repeatedly be using these two to actually do some computations. Okay, so I know I've run a little bit over, but I just want to give you a little idea how to prove these. I'll only prove number 6. The other ones are on the exercise sheet for you to prove, but it's a 2-line proof, so I'll just quickly give it to you. It's a proof of 6. So what do we do? How do we show something how do I show that the conditional expectation of this is equal to that? Well, remember my definition. My definition gave the properties that's something that I need to check in order to know something is a conditional expectation. So my strategy was guess the answer and then check that it satisfies these properties. Now here I don't need to guess the answer. I've been told what the guess is. So I just need to check that if I put z equals expected value of x, then z will satisfy these two properties. Okay, so first of all, this is just a constant, right? And so it's measurable with respect to any sigma algebra. So in particular, this is going to be G measurable for any sigma algebra. So since expected value of x is constant, it's measurable with respect to the trivial sigma algebra. So in particular, it's measurable with respect to any sigma algebra. So it is G. Okay, so condition 1 holds. What about condition 2? So it's now for condition 2. Let A be in G. Well, we know that that means that A is independent of anything in this sigma algebra. So in particular, the indicator function of A and x are independent as random variables. So what does that mean? We need to compute well, I'm going to start with the right-hand side, and I'll come back to the left-hand side. So let's look at expected value of indicator function of A. Well, because these are independent, this is just equal to expected value of x times expected value of indicator function of A. So here I've used independence. But expected value of x is just a constant, and I know I can take constants inside and out of normal expectation, and so this is just equal to expected value of x, indicator function of A, and this is since x is constant. And that's exactly what I needed to show. I needed to show that this, so replacing z by expected value of x, satisfies that. And so that completes my proof. This satisfies the two conditions needed in order to be that conditional. This satisfies the two conditions needed in order to be that conditional expectation, and so that gives me what I wanted. Okay, are there any any questions on that? Okay, so in that case, sorry, I've run a little bit over on the first session, but we'll have a 10-minute break, maybe come back at 20 past. And in the meantime, I'll be here if you want to ask me any questions. So in the second session, we'll get onto the definition of a martingale and start looking at martingale properties. Okay, so see you at 20 past. Okay, shall we get going again? So, as I said, we're now in a position to talk about what the definition is of a martingale. So here it is. So a stochastic process xt is a martingale with respect to a filtration f, which is equal to ft, t greater or equal to 0, if it satisfies the following three properties. So the first one is that xt is adapted to f. So again, just to remind you what that means. So in other words, xt is ft measurable for all t. The second property is that xt is integrable for all t greater than or equal to 0, so i.e. expected value of the modulus of xt is less than infinity. And the third property is that expected value of xt conditioned on fs is equal to xs for all 0 less than or equal to x less than or equal to t. Okay, so what do these conditions mean? Well, the main point is the third one. If we just think about what the third one means, the third one tells us that if we know what has happened with us, if we know what's happened up to a certain time s, and we want to know what are we expecting to happen at time t, we're actually expecting nothing to change. And so if you think about if xt is the wealth of a gambler who's sort of playing a continuous game, constantly betting some money, if you know how much money he's got at time s, if you know the history of the process up to time s, and you want to know what are his expected earnings, what's his expected amount of money going to be at time t, it's not going to change. And it sort of embodies what it means for him to be playing a fair game. If you're playing a fair game, you shouldn't be expecting to make money or lose money. You should expect your expected profits that you make in the future should be the same as the amount of money that you've got now. Otherwise, it's not a fair game. If it's greater or less than, then the game is biased one way or the other. So this is the important condition that really captures what it means to be a martingale. Well, why do we need the other two conditions? Well, xt has to be integrable, otherwise conditional expectation doesn't make any sense. If you remember, we couldn't even define conditional expectation unless we had that xt was an integrable random variable. So this condition has to be there in order for this definition to even make any sense. And what about the first bit? Why do we need xt to be adapted? Well, again, remember in our definition of conditional expectation, this was an fs measurable random variable. So if this is going to be equal to xs, then xs had better be an fs measurable random variable. And so again, this couldn't possibly be true unless we had an adapted process as well. So these two conditions are essentially there to make this definition make sense. And this is the absolutely critical condition that captures this idea of being a fair game. Okay, so there's So let's just sort of write that here. So property C embodies the idea of a fair game. And in particular, let's just set s equal to 0. Well, then we have, and use our Tower law. Well, if we ask us what's the expected value of conditional expectation of xt conditional on f of 0, well, that's just equal to expected value of f of t. That was just our Tower property that we had in our conditional expectation theorem. But this here is exactly equal to expected value of x0. So this is from theorem on conditional expectation. And this here is property C. So what does that mean? Well, that means that our expected money that we have at time t is the same as what we start off at the beginning. And so again, this is true for all t greater or equal to 0. Okay, so this is a really useful property of a Martingale process. It doesn't change in expectation as time increases. Okay, we can sort of adapt these definitions a little bit by changing the property C. So we say a stochastic process xt t greater than or equal to 0 is a sub-Martingale if C is replaced by I'll call it C minus, which says that expected value of xt conditional on fs is greater than or equal to xs for all 0 less than or equal to s less than or equal to t, and a stochastic process is a super Martingale if C is replaced by C plus, which is expected value of xt conditional on fs is less than or equal to xs for all s between 0 and t. Okay, so these might seem a little bit backwards to you. So somehow the sub-Martingale, your expected profit is increasing, and the super Martingale, you're sort of doing worse. So one way to remember it is, well, there's nothing super about super Martingale. So if your profit is a super Martingale, you're basically on average losing money, which is not that great. The other way to remember it is sub-Martingale, the b points up, so the inequality goes that way. The super Martingale, the p points downwards, so it goes that way. Two different ways to remember it. So yeah, just a little sort of health warning about that. It sort of feels the wrong way around, but that's the way the definitions are given. Okay, so why are martingales sort of interesting? Well, it turns out that they crop up in processes which are connected to Brownian motion. So here are some examples of martingales. So let Bt be a Brownian motion, and let F be the natural filtration, for BT. Right, then the following processes are Martingales. With respect to the filtration F. Okay, so the first one is that Brownian motion is itself a martingale. The second one is that if we take Brownian motion and we square it and subtract t, that's a martingale. And the third example is that if we look at the exponential of sigma bt minus sigma squared t over 2, that's a martingale for any sigma in the reals. Okay, so how do we know that these are martingales? Well, what we need to do is we basically just need to go through these three conditions and just check them one by one. So what I'm going to do is I'll illustrate this for property 3. 1 and 2 are on the exercise sheet for you to do for next week. Okay, so let's do that. Okay, so here are our conditions. I'll just leave them on the board for now, just as I prove each one, just so that we can remember what they are. Okay, so the first thing that we need to do is we need to check that this is an adapted process. So proof for C. So proof for part 3. Okay, so first of all we're going to check. So we're going to check A, B, and C. Okay, so for part A, let's define g of x to be equal to e to the sigma x minus sigma squared t over 2. Well, this is just a continuous function of x, and so that means that if we apply g to Brownian motion, it's going to be measurable with respect to the sigma algebra generated by BT, because we know that measurability is preserved by continuous functions. So this is a continuous function of x, and hence xt, which is precisely equal to g of bt, is sigma bt measurable. Okay, but we know that sigma bt is a subset of ft because we're using the natural filtration, and so that means that this is ft measurable, and so that gives us the adaptedness property. Okay, any questions on that? Okay, so that's part A done. Okay, what about part B? Well, we need to check that xt is integrable. So what do we need to do? Well, we need to compute that. Okay, but this is the modulus of something, and the something is non-negative because it's an exponential of a real value. So this is just equal to the expected value of e to the sigma bt minus sigma squared t over 2. Well, this is a constant, so we can pull that outside. So we can take out the e to the minus sigma squared t over 2. And again, remember, bt just has the same distribution as square root t times a normal 0, 1 random variable. So this is expected value of e to the sigma square root t z, where this is normal 0, 1. But this is just the moment generating function of a normal 0, 1 random variable. So we know what this is. So there's our e to the minus sigma squared t over 2 from the outside. This is just equal to e to the sigma squared t over 2. And these two cancel, and so we get 1, which is strictly less than infinity. And so that gives us our integrability. Okay, so just a straightforward computation. And again, with these other ones, the only thing you need to be careful about is, to take absolute values here. It's the modulus that needs to have finite expectations. So just be careful about that with the other two steps. Okay, so that's part B. And then finally, we need to do our main event. We need to check our Martingale property. Okay, so what do we do with this one? Well, we actually just need to compute expected value of xt conditioned on fs. And I'll need the rest of the board for that, so let's rub this off as well. Okay, so how are we going to do this? So this is the first kind of computation we're trying to do. We're trying to do a conditional expectation with respect to a pretty complicated sigma algebra. Sigma algebra generated by uncountably many Brownian motions up to time s. So we need to use the properties of conditional expectation from the theorem, and in particular the one that said, well, we want to try and decompose this into something that's fs measurable and something that's hopefully sort of independent or close to being independent. So let's try and do this. So we can write this as xs times the exponential of sigma bt minus bs minus sigma squared t minus s over 2 conditional on fs. Okay, so all I've done there is I'm just using exactly this expression here, and I've pulled out e to the sigma bs minus sigma squared s over 2, and then I've had to put it back in here again. So I'm just using the exact explicit expression for xs over there. But we know that xs is fs measurable. We checked that in condition A, and so we can take this outside. So this is equal to xs times the conditional expectation of sigma bt minus bs minus sigma squared t minus s over 2, conditional on fs, and this is because xs is fs measurable. Okay, but we also know that Brownian motion has independent increments. So we know that bt minus bs is independent of the whole history of the Brownian motion up to time s. So in particular, this random variable here is independent of this sigma algebra. And so that means, again, using our properties of conditional expectation, we can just lose the conditioning. And so we can write this as xs times the expected value of sigma bt minus bs minus sigma squared t minus s over 2. Okay, so we don't need to condition on anything anymore, and so this is, since bt minus bs is independent of fs. Okay, but this is just an ordinary expectation now. So we know how to do ordinary expectations. So in particular, we can write this as xs times the expected value of sigma square root t minus s z minus sigma squared t minus s over 2, where z is just an ordinary normal 0, 1 random variable. And this is exactly the same computation that we did over here. We can pull out the e to the sigma squared t minus s outside, and then this just gives us this, but with t replaced by t minus s, and so they cancel, and we just get 1. And so this is equal to xs, which is what we needed. Okay, so I've gone through that computation in quite a bit of detail to sort of really show you why we needed our conditional expectation property theorem and how we actually use it. It's all about sort of manipulating what's inside the expectation to pull out the measurable bits and sort of hopefully be left with independent bits. So we're decomposing into measurable and independent bits, and then just using our properties of conditional expectation to slowly reduce it down until we've got a computation that we know how to do. Okay, so any questions on that one? Okay, so in what follows, unless I specify otherwise, so that's sort of almost the rest of the course. If I don't tell you what filtration we're using, you can assume it's the natural filtration that we're going to be using. And in particular, if we're talking about properties of Brownian motion, you can assume it's that sort of natural filtration for Brownian motion. Okay, so okay, so now we're just going to look at just a few useful results which apply to martingales, and we'll see why they're sort of really useful. So first one is the optional stopping theorem. Okay, so we showed above that that martingales, the expectation of a martingale is constant in time. So if x is a martingale, then expected value of xt is equal to expected value of x0. And it turns out one of the useful properties of martingales is actually this is true if we can actually replace t by a stopping time, not just any stopping time, but a particular kind of stopping time. So this is true for any deterministic t, but it turns out that we can actually replace t by random t's, which are stopping times with one additional property. So this still holds. If t is replaced by certain stopping times. Okay, so here's the statement of the optional stopping theorem. Okay, so let xt be a martingale. And suppose that t is a bounded stopping time. So what does that mean? That means that the probability that x is less than or equal to k, probability that t is less than or equal to k is equal to 1 for some finite k. So in other words, it's a stopping time, but I know it's going to happen by a certain time. So for instance, I know it's going to happen before time 5 or something like that. then what do we know? Well, then expected value of our martingale at time t is just equal to the expected value of the martingale at time naught. Okay, so it exactly tells us that we can replace this by that. And the key point is we need t to be bounded. So this doesn't work for any stopping time. It needs to be a bounded stopping time. And just for those of you who've seen this theorem before, you may have seen versions of this theorem with slightly different sets of conditions. This isn't the only version of it. You can sort of put extra conditions on the martingale, and that allows you to relax the conditions on the stopping time. But this is the sort of simplest version of this theorem. Okay, so let's see how we use it. So here's was that a question or no? So here's an example. And this is the so-called gambler's ruin problem. Okay, so if you're a gambler, one of the things that you might want to know is you might be sort of gambling to make a certain amount of money. So supposing I want to buy a car. So I'm going to decide, okay, my car costs 10,000 francs. I'm going to gamble until I've got 10,000 francs. But I'm actually only willing to lose 5,000. So I'm not completely crazy. I'm going to start gambling, and if I lose 5,000, I'm just going to give up. If I make 10,000, I'm going to stop as well because I'm going to buy my car. And the question that you're interested in is, what's the chance that you get to 10,000 before you've lost 5,000? That's the sort of thing you want to know is, what's the chance that you make your target before you sort of lose the money that's become your sort of lower bound? Okay, so let Bt be a Brownian motion. So suppose these are our winnings are given according to a Brownian motion, or winnings and losses. And for A between 0 between B, let TA and TB be the hitting times of A and B. So remember, we defined this in the last lecture. The first time that your Brownian motion hits level A is TA. The first time that your Brownian motion hits level B is TB. And if you never hit A, TA is infinite. If you never hit B, TB is infinite. Okay. And finally, let T be the minimum of TA and TB. So I think I showed you this notation in the last lecture. This is the minimum of these two. So this is be the first time so this is the time that Bt first exits the interval AB. Okay, so what we want to know is we run our process, we sort of gamble until we first leave this interval. What we want to know is what's the chance that we left it at the higher point rather than leaving at the lower point. Okay, well, I've said I'm going to use the optional stopping theorem, so we need to know that these things are stopping times. So we know that TA and TB were stopping times. I sort of argued this in the last lecture, and now with the formal definition you can check it. And it's also possible, it's not too difficult to check that T itself is a stopping time. So that's an exercise. So the minimum of 2 stopping times is also a stopping time. So T is a stopping time. So this is an exercise. Is it a bounded stopping time? So what do people think? Who thinks T is a bounded stopping time? Anyone? Who thinks it's an unbounded stopping time? Okay, so you're absolutely right. There's nothing stopping our Brownian motion just sort of sitting between these intervals A and B and just never exiting it. And sure that the probability gets smaller and smaller as time goes on, but there's always a chance that we might not exit it. So in particular, there's no constant time k by which I can guarantee we can exit. I can't tell you, oh, by time 100, we're definitely going to have exited that interval. So this is not a bounded stopping time. So this is a bit of a problem, right? I mean, we've got a martingale here, we've got a stopping time, so it looks like we're set up to use optional stopping, but it's not bounded, so we have a problem. Okay, so any ideas?
To cut at some time and then time.
Yeah, that's right. So let's replace t with the minimum of t and some fixed value little t. Then we have a bounded stopping time. Apply the optional stopping theorem with that, and then let little t go to infinity and see if we can get something. Okay, so so let's just write this down. So okay, now t is not a bounded stopping time. But we do actually know that it's finite almost surely. Although we do know that the probability that t is strictly less than infinity is equal to 1. How do we know that? Well, you actually proved that on the exercises that were for this week. You showed that probability that ta was less than infinity was equal to 1. And this is strictly smaller than TA because it's the minimum of these two. And so essentially you proved that. So this was last week's. Exercises. Okay. However, we can do this idea. We can replace t by the minimum of t and some constant time. So however, for any t greater than or equal to 0, the stopping time minimum t is bounded. Well, what's it bounded by? Well, it's bounded by little t, just by definition. The minimum of little t in anything is smaller than little t. Okay, and so we can apply optional stopping theorem to this stopping time and this martingale. Okay, so using that Brownian motion is a martingale. We know that expected value of b t min t is equal to expected value of b0. But we know for Brownian motion, b0 is always equal to 0, and so that's equal to 0, and this is true for all t greater or equal to 0. Okay, well let's how's this helping us? Well, let's analyze this left-hand side a little bit. So there's sort of three possibilities with this left-hand side. So either this can be equal to TA, in which case this value is equal to A, because Brownian motion at its exit point for A is just equal to A. Or this can be equal to TB, in which case the whole thing's equal to B, or it can be equal to T. So let's split into those cases. So 0 is equal to expected value of BTA times the indicator function that T min T is equal to TA, plus expected value of BTB times the indicator function that T min T is equal to TB, plus expected value of BT times the indicator function that T min T is equal to T. Okay, so that's just breaking that into 3 events. Well, we know what each of these is equal to. This is just equal to A on that event, so we can pull that outside, that's a constant, times the probability of this event. Well, this event occurs when TA is less than or equal to TB min T. Similarly, this is equal to B times probability that TB is less than or equal to TA min T. And this one is equal to expected value of BT times the indicator function that T happens after time T. Okay, so now it's kind of reasonably clear what we want to be doing. We want to be getting a handle on this kind of event. And so if we let T go to infinity, this probability is going to converge to that. This probability is going to converge to that, which is just the complement of this. So we need to know what happens as we let T go to infinity over here. Okay, and we're kind of hoping it's going to go to 0, right? Because we sort of think that this event just isn't going to happen, right? We know that T is finite, so as we let little t go to infinity, this event should get smaller and smaller and smaller. The trouble is this can get bigger and bigger and bigger potentially. But let's just see how we can take control of this. So let's have a look at how big this can be. Okay, well this is less than or equal to, we can just take the modulus inside, so expected value of BT times the indicator function T is bigger than T. But now something useful happens, right? If we know that the stopping time hasn't happened yet, we know that this is still inside the interval AB. And so actually this can't be too big. This must be less than or equal to the maximum of mod A and B times the probability that T is bigger than T. Because we know that with the stopping time hasn't happened, we know we haven't exited this interval, and so this is actually bounded. And now if we let T go to infinity, this bit tends to 0, that bit's bounded, and so the whole thing tends to 0 as T goes to infinity. And so letting T go to infinity in this whole thing, so therefore 0 is equal to A times probability that TA is strictly less than TB. They can't be equal, so I can lose that less than or equal to. You can't exit at A and B at the same time because one's greater than 0, one's less than 0. This bit becomes B times 1 minus probability TA less than TB. And this bit was 0. And so rearranging this, we get probability that TB is less than TA is just equal to mod A over mod A plus B. Okay, and now you can see whether you're going to, whether you're more likely to sort of make your target or not. It sort of depends on the ratio between your things. So if your target amount of money is greater than the margin you're willing to lose, then you're more likely to sort of exit with a loss. And if the target amount of money is smaller than the amount you're willing to lose, then you're more likely to exit by having made that target. Okay, so this sort of just gives you an example of how this optional stopping theorem is kind of powerful. It wasn't so clear how just knowing a result like this actually allows us to do this sort of computation. And again, there's more exercises on the example sheet to sort of show you some other things that you can do with the optional stopping theorem. Okay, so I'm just going to quickly finish just in the last kind of 2 minutes, just with a sort of list of properties of martingales. I'm not going to prove any of them, but just some sort of inequalities and convergence results which hold for martingales, which are going to be useful later on in the course. So again, as I said, I don't prove any of these, but any textbook on on Martingales will give you the proofs. Okay, so Martingale inequalities. And convergence theorems. Okay, so first theorem is Dub's maximal inequality. Okay, so let xt be a Cadillac Martingale. Are you all happy with Cadillac? No. So this is right continuous with left limits. If you want, you can just replace this with continuous. But the results a little bit stronger than that. So it just allows you to have processes which can have a jump and then they're right continuous. So. It's from the French, so continuer à droite, limite à gauche. So we've got a Cadillac Martingale, or it can be a non-negative sub-Martingale. Then, for all lambda strictly bigger than 0, the probability supremum of s less than or equal to t, xs being greater than lambda, is less than or equal to lambda to the minus 1, expected value of the modulus of xt. Okay, so this one is very useful because the left-hand side is the supremum over uncountably many random variables, and the right-hand side only depends on one random variable. So if you just had that, this would look a lot like Markov's inequality. The key point is that we can put the supremum in there. That's what makes this a really powerful result. Next theorem is Dub's LP inequality. Okay, so let xt be as above. So Cadillac Martingale or non-negative sub-Martingale, but expected value of xp being infinite as well for all t, so it's got finite pth moment. Then for all p strictly bigger than 1, the expected value of the supremum of s less than or equal to t, xs to the power of p, all of this to the 1 over p is less than or equal to p over p minus 1, expected value of xt to the p, all of this to the 1 over p. So this is the sort of LP norm of xt, and so essentially you're saying the LP norm of the supremum of xp is only a constant, it's sort of bounded modulo a constant by the LP norm. And again, the key point here is that you can take the supremum outside and it only costs you p over p minus 1. So for example, the L2 norm, if we took p equals 2, it costs us a factor of 2 to be able to get rid of this supremum. Okay, and then just one last theorem, which is the Martingale convergence theorem. So there's two parts here. So the first one is let xt be a Cadillac martingale which is bounded in L1 so this here is bounded in LP. So we just need to be bounded in L1. Then xt converges to x infinity almost surely for some if infinity measurable x infinity, where this is the union of all of the FTs that we had in our filtration. Okay, but the key point is here is that a real sort of useful property of martingales is if we know that martingales are bounded in L1, we know that they converge. Now, in general, that's not true of other processes. Just knowing that a process is, if you just take a typical stochastic process, there's no reason why it should converge almost surely as t goes to infinity. It can sort of go all over the place. This one tells you that it isn't. Sorry, this should be less than some k. Okay, and then just the very, very last convergence theorem that I want to give you. So in particular, actually, if you think of Brownian motion, that fails, right? Because if you think of Brownian motion, the L1 norm looks like square root of t, and that's not bounded in L1. As t goes to infinity, that goes to infinity. So Brownian motion does not converge almost surely. But if we had a sort of decaying form of a decaying martingale, or martingale that isn't going to be blowing up like t, then it will have some limit. And finally, the last thing I'm going to say today is let xt be a Cadillac martingale which is bounded in LP for some p greater than 1, then xt tends to x infinity almost surely and in LP. So if we look at xt minus x infinity and raise the power of p, and take that to the 1 over p, that's going to tend to 0, and moreover xt is actually equal to the conditional expectation of x infinity conditional on ft almost surely for all t greater than or equal to 0. Okay, so that tells you about the kind of processes which can be LP martingales. They're essentially all conditional expectations of some infinity measurable, if infinity measurable, random variable. Okay, so I think that's everything I'm going to say about martingales. So next week we're going to start defining, and we're going to do some stochastic calculus. So we're going to define the stochastic integral and start looking at properties of that. Okay, so before I stop, just any last questions?
What is f infinity?
Okay, so what this is exactly the union of t greater or equal to 0 ft, and this exists because these are increasing sigma algebras. So you can sort of think of this as the limit as t goes to infinity. This contains more and more information, and it's a sigma algebra in its own right. Okay, but yeah, good question. Any other questions? Okay, so see you next week for stochastic calculus.